potential difference. So we'll start by defining what is current. We already discussed it in 10a. However, we need to go a little bit further and come up with an absolute definition, which will actually later help us develop an equation for that as well. Alright? So current by definition is the amount of charge passing a point each second. So the amount of charge passing one single point every second. Alright? We measure the current in amperes, or capital A. If you were to write 2A, that's 2 amperes. And we measure the current using an ammeter. Now it says here in series, and it also says in brackets, low resistance, so it doesn't affect the circuit. So let's just understand what that means, what's going on. If you want to measure the current, we use an ammeter. That's the component that you use, and we add the symbol in 10a that you need to be able to draw. Where does it go in the circuit? The ammeter is specifically measuring the amount of current passing through that circuit. So it has to be in the circuit with it. However, what it can't do is, whilst it's allowing current to pass through itself, it cannot affect the amount of current that's passing through, because otherwise then that becomes a new component which also may need to take a share of the voltage. So the ammeter has to have the lowest resistance possible so that as current is passing through it, it does not affect the amount of current that passes through the whole circuit every second. So that's why an ammeter goes in series, so that it can actually measure what's coming through, but it must have the lowest resistance possible so it's not affecting the actual current, it's just taking a measure. It's not actually becoming part of the circuit. Potential difference, it's a new way of saying voltage. Potential means between one point and another, there's a difference in energy. Just like gravitational potential. You have a height, you have energy stored, and you have that potential energy ready to be transferred into other forms. So potential difference is just voltage. It's the difference between the positive and the negative terminal, and it's a measure of the amount of energy that is transferred to each coulomb of charge. And coulomb and charge is something we move on to in the next section. But so you have a definition of voltage and potential difference. It's the amount of energy transferred to each coulomb of charge. Now, more simply, it's how much energy is transferred to the electrons by the supply, and then how much of that electrical energy is actually transferred at each component. So you also may hear the expression voltage drop. Each component takes a specific potential difference. It has a specific voltage, and that's come from a supply. So the voltage drop is what is being taken from the supply for each component, i.e. how much energy is being transferred at that component, and what about that component from the supply. It's measured in volts, which is nice and easy. The greater the potential difference across a component, the greater the energy transferred, because we've said potential difference is essentially a measure of energy transfer, but per charge as well, which we'll look at in the future. Measured using a voltmeter in parallel across a component. So it's the opposite of an ammeter. Ammeter goes in series in the circuit, and it has a very low resistance so that it doesn't affect it. A voltmeter, on the other hand, must be placed in parallel around the component or the section that you want to know how much energy is being transferred at this point, at this component. So you put the voltmeter, you connect one part before the component, one part after the component. It's on the outside of the circuit, so it's kind of outside looking in. What went in terms of energy, and what came out will tell you how much energy has been transferred in that component itself. So it has to be from an outside perspective, and in that case it must have a very, very high resistance so that no current passes through the voltmeter itself. Again, opposite to the ammeter. You do not want current going around the circuit then going through the voltmeter as well as the component, because then how do you know how much voltage is being dropped or how much energy is being transferred in the component itself? The voltmeter has now become a part of the circuit. So that high resistance in the voltmeter sends the current straight past, goes straight through the component. If it's so high, it won't even bother going through the voltmeter. It wouldn't even be able to pass through. The resistance would be too high. And that means that it doesn't affect the circuit again. Okay? Two conditions, very simple. You must have these two conditions if you want to produce an electrical current in a circuit. Number one, you have to have a potential difference. There must be a positive and a negative transferring energy to the electrons, causing that attraction from one side negative to the positive. Without that attraction, they don't move, they don't flow. Secondly, as a result of that, you have to have a closed circuit. If the circuit is not closed, then they won't feel that attraction. So you may have the potential difference, but if you cut that circuit with a switch or it breaks, then it won't feel the attraction, and therefore again the current will not flow. So two conditions. You must have a potential difference, you must have a closed circuit. Moving on, looking at circuits again, both series and parallel, but they're in what we call combination circuits. So these are the hardest circuits that you will see in a GCSE physics exam on electrical circuits. So you could either have a series circuit where you apply the rules that we looked at in 10A, you could have a parallel circuit, same again, or they could be quite mean and they could give you a combination of both series and parallel. This one specifically, if you have a look, you've got a series loop with a bulb there and then a parallel section. So we'd say this is a series circuit technically, it's just got a parallel section in there. And then obviously if you have a look at this one, you can see this is very similar to the parallel circuit, but again here, you have two bulbs in series. So this one would be a parallel with series, this one would be a series with a parallel section, and this one is just a very difficult example of this same circuit. We just have an extra parallel section with three bulbs this time. Okay? So, starting with this one, what do we need to know? You have to be able to determine what is the current through the circuit at different points, and what are the potential differences across the components in a combination circuit. Alright? And the simple series and the simple parallel as well, but we know the rules for those. So, looking at this as a series, the easiest way to say how do I deal with this parallel section, which rules apply to which part. First we assume this is a series circuit, so it has two components. We know that two components in a series circuit share the supply somehow. We need to know what share of this 10 volt supply will the single bulb take and what will the parallel section get. Okay, so we're just going to split this supply into two, component 1 and component 2. Although there are two bulbs, we're going to assume the parallel section is one component. So, if it's shared between the two, quite clearly component 1 and component 2 are not identical. So the resistances must be different. Now this is one bulb, this is two bulbs in parallel. This again is something you'll learn a little bit further on in resistance on 10C, 10D. Okay? That a parallel section has less resistance than just a single component. So if you have a single bulb here and then you add the same bulb in parallel to a new section, this parallel section actually has less resistance than the single bulb because there are more pathways for the current to take. It's much easier to run down two lanes than everyone run down one. If the current is all going through this one bulb, it's going to be a lot harder than if it can go, some go this way, some go that way. So this parallel section has lower resistance than this one. We know in series, if it's lower resistance, it takes less of the share. Specifically, this is half the resistance of this single bulb. So if this is 2 times the resistance of this section, this gets 2 times the voltage. So we have to split our 10 volts into 3, 2 to 1, so 3. This one will therefore get 6.6, 6.7 volts, so 10 divided by 3 into 3 parts is 3.3, 3.3. So this one gets 2 times this, so 6.6 for this bulb, so the voltage here, 6.7 in round, and therefore this section here is 3.3. Now, volts. That's dealt with. The voltage drop across this single bulb is 6.7 volts. Okay? We've said that the parallel section gets 3.3 volts. However, what does each bulb get? Now, if we think back to the parallel circuit, the rules, each branch takes the maximum supply voltage. Now in this case, it's not going to take the maximum supply because it had to be shared. However, each branch in this section takes exactly the same as what the first one gets. So if this section gets a 3.3 volt share of the total, then every branch in this parallel section gets that 3.3. The total is only made up of the 1 and the 1. Remember, you don't add parallel branches to make the total again. The total comes from the single bulb and just one of the parallel in this section. So your split of voltage is 6.7, 3.3, but each parallel one here gets 3.3 as well. Current is very straightforward. Current around the circuit where there's no parallel, it's the same everywhere. So it's 2 amperes through this one, but it gets to a junction on this one, and therefore it splits. Because these two bulbs are identical, it splits 50-50. So 2 amperes splits at the junction, 1 ampere through the top bulb, 1 ampere through the bottom bulb, and then obviously rejoins, you get your 2 amperes back here and all the way around. So that's the first series circuit with a parallel section and your combination. A different circuit you could get for the combination is a parallel circuit with series within. This is a little bit more straightforward actually. So you have a parallel branches here, but on the top branch you have 2 bulbs in series. So if we look, we've got a 10 volt supply again. Thinking about our parallel rules, each branch gets maximum supply. So this branch here has 10 volts. This branch here also has 10 volts. However, this branch has to share its voltage, because it's series on the branch, has to share its voltage between 2 identical bulbs. So this one gets 5 and this one gets 5. So 5 volts, 5 volts, but the bottom one, as it's on its own, on its branch, it gets the maximum supply. So 10 volts this one, 5 and 5 for the 2 on the same branch, they're shared. In terms of brightness, this one is maximum brightness, these two are half the brightness. Same on this one, it's not quite maximum, it's actually less than this, because that's 10 volts, that's 6.7. So it's definitely brighter than these two, in fact it's twice as bright as these two are the same brightness, but this one is still less than this because this has the maximum 10 volts, whereas that only got 2 parts of a 3-part share. Current splits at the junction again in parallel, so 3 amperes coming in. It splits, but it doesn't split 50-50 because the current splits at a junction based on resistance. But this path has 1 bulb, this path has 2 bulbs in series. The resistance of this branch is twice as high as the resistance of this branch. There are 2 bulbs to pass through, it's twice as hard to get through. So if this has a higher resistance for the current split in a parallel, it will take less current. Alright? Because this path is easier to flow through, lower resistance, higher current. Specifically, what's the ratio? This is 2 times the resistance, so this gets 2 times the current. So it's 2 to 1. So if I split 3 amperes 2 to 1, very easy. 2 amperes comes down this branch, and just the 1 ampere through this one and this one. Now, one thing that a lot of people do, and they make a mistake on this part, you've split the current at the junction. You've figured out correctly what's the ratio of current through each branch. But then this is now effectively a series branch, and remember, current is the same everywhere. So if 1 ampere goes down this branch, 1 ampere goes through the first bulb, and 1 ampere goes through the second. It's not 0.5 and 0.5. On this branch, it's 1 ampere everywhere. On this branch, it's 2 amperes everywhere. It then rejoins at this junction again, and you have your 3 amperes back to your supply.